of this tutorial is to learn how to process Sentinel-3 data. You will be introduced to Sentinel-3 mission, its products, and the processing steps to visualize several spectral composites from all-C data and compute spectral indices with synergy data. The main objective of Sentinel-3 mission is to measure sea surface topography, sea and land surface temperature, ocean and land surface color with high accuracy and reliability to support ocean forecasting systems, environmental monitoring, and climate monitoring. Sentinel-3 satellites carry 4 instruments: ocean and land color instrument, sea and land surface temperature radiometer, synthetic aperture radar altimeter, and microwave radiometer. The mission is composed of a constellation of 2 satellites, Sentinel-3A and Sentinel-3B, flying in the same orbit but separated by 140 degrees. The 2 satellites enable a short revisit time of less than 2 days for OLS and less than 1 day for SLSTR data at the equator. Sentinel-3 products are available in product dissemination units to ease online dissemination and data handling from users. The product dissemination unit is a portion of data and is defined per product type. 3 kinds of product dissemination units are defined: frame, stripe, and tile. A frame is identified by a fixed reference system. The along track coordinate identifies the product frame start point with respect to a fixed orbit position. Each frame is stepped by a constant time interval along the orbit track, and the along orbit cycle coordinate identifies the relative orbit number within the orbit cycle. A stripe coincides either with the acquisition dump or with a defined acquisition time segment, whose length may differ according to the instrument type, for example, full orbit pole-to-pole or half orbit. A special case of stripe is provided by the vegetation-like product called VGT-P, where the stripe is mapped on a plate carrier geographical correction. Tiles are defined only for vegetation like 1 or 2 day synthesis products. VGT S1 and VGT S10 provided on a plate carrier map projection. A tile corresponds to a geographical subset of the synthesis image, as you can see in this image. The Sentinel-3 instruments and combined products are ocean land color, from ocean land color instrument sensor. We have the following products for level 1 and level 2. This optical instrument is used to provide data continuity for MBSAT MERIS instrument. It is a possible imaging spectrometer that measures solar radiation reflected by the Earth. The primary objective of OLSI products is to screen the ocean and land surface to harvest information related to biology. OLSI also provides information on the atmosphere and contributes to climate studies. So let's talk in more detail about these products provided by the OLSI instrument. Level 1B products are top of atmosphere measurements, radiometrically corrected, calibrated, and spectrally characterized. It is quality controlled, orthogeolocated, and annotated with satellite position and preliminary pixel classification in order to mask land, water, and clouds. Products are generated for the whole globe with the same coverage in full resolution of 300 meters and reduced resolution of 1.2 kilometers. There are also level 2 land data. This product consists of land and atmospheric geophysical parameters derived from the processing of measurement data provided in Level 1 product computing for full resolution and reduced resolution, and also the water component, which consists of water and atmospheric geophysical parameters. Next is the sea and land surface temperature. The principal objective of these products is to provide global and regional sea surface temperature and land surface temperature to a very high level of accuracy for both climatological and meteorological applications. The Sentinel-3 SLSTR data products include Level 1B products which provide radiances and brightness temperature for each pixel in a regular image grid, and Level 2 data for land and water, which provide temperatures for sea and land surface. Next is the surface topography mission. The principal objective of this product is to provide global and regional sea surface temperature and land surface temperature to a very high level of accuracy for both climatological and meteorological applications. These data products include Level 1B, which provides Level 0 data corrected for instrumental effects and calibrated multi-looped and slant rates corrected data. Level 2 products for land and water provide Level 1 data which are corrected for geophysical effects and provide land products and water products respectively. Also, we have the synergy products. Also, in conjunction with SLSTR data, delivers the synergy products, providing continuity with spot vegetation. The primary objective of synergy products is to monitor land use. Synergy also provides information relating to worldwide food security and contributes to the study of climate. Sentinel-3 Synergy includes also Level 1 full resolution and SLSTR Level 1 radiances and brightness temperature products. Level 2 processing aims to combine information and from the Olsen SLSTR instruments to provide improved data for land surface analysis. There are 8 products available to users: surface reflectances and air resource parameters over land, 1 kilometer vegetation-like products from top of atmospheric reflectances, surface reflectance over land, 1 kilometer vegetation-like product of 1-day synthesis, 1 kilometer vegetation-like product of 10-day synthesis, and the aerosol optical depth products. Sentinel-3 products can be grouped to different types based on delivery time to users. The selection of a product type in terms of delivery time is a trade-off between real-time needs and the final accuracy needed. The delivery product types are near real-time, which are delivered less than 3 hours after data acquisition and mainly used for marine meteorology and ocean atmosphere gas transfer studies. Data products are 10 minutes in length. Next we have short time critical, which are delivered within 48 hours after data acquisition. due mainly to the consolidation of some auxiliary data, like preliminary orbit data, and the data are mainly used for geophysical studies and operational oceanography. Data products correspond to half-orbit information. And finally, we have non-time critical data which are delivered within 1 month after data acquisition. This additional delay allows consolidation of some auxiliary data like precise orbit data, and the data are mainly used for geophysical studies and operational oceanography. These data products correspond to half orbit information, in other words, pole to pole. Next, we have the naming convention. In order to understand, in order to extract some information from the file names of the datasets, here you can see the file name convention of ONS dataset. First is the mission identifier, from which satellites the data were acquired. The name of the instrument where data were acquired, here is also. The processing level is the third term of the file name. The data type, if it's full or reduced resolution. The start time and the stop time of the acquisition. The date where the products were processed. The duration, cycle number, and relative orbit number. The code of the processing center. And also lastly, there is some information about the timeliness, if we have near real time or not critical data. Similar cases are also for SLSTR and Synergy. And here we have an example of a name to understand better the naming convention. Here it is a dataset we will use for our tutorial. It is an OLSI data product. It was acquired on August 25, 2022. It is a level 1 product. In other words, top of atmosphere agencies at full resolution, as you can see here. This dataset includes data from Finland, which is the study area of Pilot 5. In order to download Sentinel-3 data, you can this Sentinel-3 data are available through Copernicus Open Access Hub. Here you can see the area of interest defined on the map and the values that we have to fill in order to find the required dataset. Also, the parameter values for querying Sentinel-3 data through umbrella application are provided. So next we have to upload several Python modules in order to apply our processing. Zip file, netcdf for library, matplotlib in order to plot our data. So next we are going to inspect the data that we were downloaded. In my case, I downloaded an OLSI dataset, an SLSTR for land data, and the Synergy. First, we are going to process the OLSI dataset.
In contrast to Sentinel-1 and Sentinel-2, where we can read them directly from the zip file, Sentinel-3 data must be extracted from the zip file in order to be read. So we extract them with the zip file library, and then we can inspect the contents of the file with the manifest file, which have an XML extension file. Here we have the commands in order to display all the contents. The radius is for all bands and some additional bands for the coordinates and the sensor angles, the quality flags, etc. Here you can see the descriptions of all the bands included in Sentinel-3 also. And next we are going to read some of these bands which are defined here. We look through all the bands and read only the needed bands. In order to read the bands, we use the dataset function provided by NetCDF4 library. Here we have to define the path to the band file and also define the variable which is similar to the name of the file. And next we are going to normalize the data we've read in order to make several RGB composites like the natural color with these three bands, the three stimulus, the natural color broadband, which is also log scaled, and the false color. Here we have the plots of the four RGB composites. And next we are going to plot them as geolocated. In order to succeed, we have to read also the latitude and longitude information from the geocoordinates file. And here it is the setting in order to plot the geolocated dataset. It is projected in a Mercator projection system. And next we continue with the processing of the synergy dataset. We also have to extract them from the zip file. We can inspect the contents of the file by reading the manifest XML file with these commands here. And here you can see the file names and the description of each one. And for the purpose of this tutorial, we're going to compute the normalized difference water index, where the one band is included normally in all data set, and the other, the short wave infrared band, is included in the SLSTR dataset. So it is more convenient to use the synergy datasets where both datasets are included. We need to read the flags datasets, which include the cloud masks. In order to mask the cloud cover pixels, the geolocation in order to have geolocated results, and the type points also file, which includes some of the geometry, solar angle values, and sensor zenith angles in order to mask out pixels with angles that which are not efficient for the computation of NDWI index. So here we search for these files and we read the needed bands, also with the dataset function. So here, yes, as you can see, the half of these bands have different dimensions. Solar zenith angle and sensor zenith angle, also the latitude and longitude have reduced dimensions. And here next we have to find which latitudes and longitudes have solar zenith angles greater than 73 degrees and sensor zenith angle greater than 50 degrees in order to exclude the respective pixels. Here you can see that the unmasked dataset has these coordinates, the minimum and maximum latitude, and the second row is the minimum and maximum longitude. And here we can see in the corrected that we don't have pixels with greater than 73 or 50 degrees zenith angle, so we can continue. Here we have a function where we can define the area of interest and compute the columns and rows in order to subset the data sets. Here we have defined that minimum and maximum longitude will be 25 and 25.5, and for the latitude and the minimum will be 66 and 65. And based on the computations, here are the pixel coordinates, the minimum and maximum column, and the minimum and maximum row of the images, which are used here in order to use a smaller subset of this dataset. And here it is the function, the command in order to compute the normalized difference water index. We have to transform the data to float type. And here we also mask the results with the cloud mask included in the flags dataset. And here it is the final result of the normalized difference water index. The white areas are cloud covered pixels. And next we can see here how to reproject this result to UTM zone 34 north. In order to do it, we have to loop through all the values and convert them with the UTM from lat-long function. And then we store them in a data frame in order to create a virtual raster with GDAL and rasterize them. We have to define the code of the UTM zone, which is 32634. We assign the resolution to 400 and the node data value to minus 9,999. And here you can see the final result, very projected rasterized NDVI map. So this is the end of the first tutorial. And we continue with the tutorial on Sentinel 5P processing. The objective of this tutorial is to learn how to visualize Sentinel 5P data and retrieve values for specific locations. Further processing steps which are required for multi-temporal processing are also explained. The processing is implemented in Python with XArray library. Additionally, the HARP component of VS's atmospheric toolbox is introduced to prepare Sentinel 5P data for multi-temporal analysis. So we will start with an introduction of Sentinel 5P mission. Is a Sentinel 5 precursor represents the first atmospheric composition mission in the frame of the European Earth Observation Program Copernicus. It provides routine observation of atmospheric trace gases, aerosols and cloud distribution affecting air quality and climate. Sentinel 5P was launched in October 2017 and aims to fill the data gap and provide data continuity between the retirement of the Envisat satellite and the NASA Aura Omeo mission and the launch of the upcoming Sentinel 5. The satellite single payload instrument, the Tropospheric Monitoring Instrument, TROPOMI, is a post-Brom imaging spectrometer with a wide field of view allowing global daily coverage. It provides continuous high-resolution spectral measurements in ultraviolet, visible and near-infrared and short-wave infrared bands. The instrument's worth is approximately 2,600 kilometers on the ground, ensuring a global daily coverage. Given the high spatial resolution of typically 7 by 3.5 square kilometers, TROPOMI enables sampling of small-scale variability, specifically in the lower troposphere. Sentinel 5 precursor orbits includes formation with the NOAA SOME mission to benefit from the high-resolution cloudy formation provided by the VR's instrument. The combination of high spectral resolution, high spatial resolution, and daily global coverage enables TROPOMI to study troposphere variability, covering a number of relevant atmospheric constituents, including ozone, nitrogen dioxide, carbon monoxide, methane, sulfur dioxide, as well as aerosols and cloud properties like cloud pressure and cloud fraction. Here you can see Sentinel 5 data products, which are available systematically and continuously over the full operational lifetime, which is expected to last about 7 years. All data are free of charge to the end users, including the general public, scientific and commercial entities.
Data products from Sentinel-5 Tropomi instrument are distributed to users at two levels from the Sentinel-5 pre-operations data hub. We have level 1B, which provides geolocated and radiometrically corrected top-of-the-atmosphere Earth radiance in all spectral bands, as well as solar irradiance. And we also have the level 2 products, which provide atmospheric geophysical parameters in line with the needs of numerical forecasting systems. Level 2 products are also to be supplied within 3 hours after sensing. This near real-time service delivers products from ozone, sulfur dioxide, and nitrogen dioxide, formaldehyde, and carbon monoxide, as well as vertical profiles of ozone cloud and aerosol distribution. In addition to the near real-time service, an extended list of products is also supplied in not time critical or offline, taking advantage of increased accuracy achieved when specific operation steps can be made with less constrained time. Next, we have the naming convention of Sentinel-5P. We can get several we can get many informations from here. The data, the timeliness of the product, if it's near real time or offline, the product level, the acquisition time, the here you can see a list with the product description, descriptors, and this description. For this tutorial, we're going to use a dataset covering a dataset included data from Balearic Islands, which is the study area of Pilot 3. We can download the required dataset from the Sentinel-5P pre-operations data hub. Here it's the area of interest defined on the map, and the parameters that are filled in here in order to download several nitrogen dioxide datasets for the multi-temporal analysis. Next, we have to load a few Python libraries, matplotlib, cartopy for the projections, xarray in order to read the netcdf Sentinel-5P datasets, and several other libraries. So here we are going to read an offline nitrogen dioxide dataset. As you can see here, we defined the pattern in order to search for the specific datasets. And in my case, I have 8 products downloaded. And next we can get with the xarray open dataset function some global attributes of the dataset. If we define as a second argument on the open dataset function the group argument, if we define the group as metadata granular description, we can get also some additional metadata like the acquisition of the data acquisition, if the dataset is offline or near critical, for example, and the product NA. If we define the group variable as product, we can read the data for every air pollutant measured by Trepometer. Here we can see the variables included in the dataset, which include the latitude and longitude, the quality layer, the nitrogen dioxide tropospheric volume and precision, and several other auxiliary data which can be used for further processing of this of the nitrogen tropospheric volume. In order to access the variable, we have to define its name here, and we can also get its dimensions, coordinates, attributes, and values with these commands here. Here you can see that the nitrogen tropospheric volume is measured on as mole per square meters. We have also the factor in order to multiply these data sets in order to convert them to molecules per centimeters per square centimeters, and several other attributes. And here we see a plot of the nitrogen dioxide vertical column. And next we can see an orthographic projection of the dataset. Next we have to filter the data in order to ensure that our measurements are correct. We have to mask out the pixels which are defined to have a quality value less than 75%. Here you can see the quality flag layer. Here you can see the red areas have very low quality values, so we have to mask out them. And here you can see the masked out data. Next, we have a new plot where the data set is subsetted to the area covering only the area around Balearic Islands, as you can see here. And next we have an example of how to extract the pixel value for a specific location. Here we have the coordinates for Palma. In order to get the pixel value, we have to find the nearest point in data by using the Harvard-Sine formula to find to compute the distance and find the minimum, the pixel with the minimum distance. And here we see the value for Mallorca. And next we continue with the multi-temporal Sentinel 5 processing by using the HARP component of the atmospheric toolbox. In order to make a multi-temporal processing, we have to make all products have the same grid. So we have to rasterize them again to a single grid in order to perform the processing. So HARP Toolbox provides a very simple and easy function to perform it. We only need to define the subset, the minimum and maximum latitude and the longitude, and also the resolution we want for our grid. We also have to define the operations. What we're going to do, we want to extract the tropospheric nitrogen dioxide column, which must be masked, which have to include only the high quality pixels. We need also to store the latitude and longitude information. We also need to convert the results to molecules per square centimeters. And the bin spatial is the command we have to include in order to specify what we defined as the subset and the resolution for the grid we need. Next is the reduce operations, where we define that the latitude, longitude, and longitude bounds are the same for all the products, except the time. And the bin function performs the actual merging, which is the averaging in the time dimension. Here we gather all the data sets we need to average, and here is the final command with the arguments, the files in which are the products we want to process, the operations which were defined here, and the reduce operation which defines which parts will be averaged. This command stores the average of nitrogen dioxide in this file here. And next we are going to read the results and plot them with matplotlib, and here you can see the final results, which is the mean, the average of a weekly average for Balearic Islands and the around area. And this is the end of the second tutorial. Any questions?
Hello, Maria.
Hello.
This is Victor from ProDevelop. I've seen that you have using the HARP functions. Don't you? You are not using any of the snap functions in this procedure?
Yes. Snap is only for Sentinel 1, 2, and 3. For Sentinel-5 processing, there is the ESA atmospheric toolbox. which
Okay,
we can use.
Harp is part of the suite, no?
Yes.
Okay. I have some. The last part is you have made the average from 1 week of observations.
Yes.
Okay. Okay, thank you.
So since we don't have other questions, we can conclude. The Jupyter Notebooks will be provided to you. And if you have any other questions, you can send them to me directly. So have a nice day and happy weekend. Okay, bye.
Thank you
Thank you
very
very
much.
much.
Okay,
Thank
thank
you.
Thank you. Bye.
Bye-bye.
you. Weekend.
Bye.